So we basically talked about this process of force and field and relationship between force and field. We said that a stationary particle creates an electric field, and another electric charged particle in an electric field created by some other particle experiences a force. In the case of magnetic field, a moving charged particle creates a magnetic field, and a moving charged particle in the magnetic field experiences a force. You see the similarity between the magnetic field created by a moving particle, moving charged particle, and electric field created by a stationary charged particle. And you see that instead of 1/4 pi epsilon naught, we have mu naught over 4 pi, and we have q over r squared in both cases. But here we have r hat, here we have v cross r hat. That creates some complications. We said that when the charged particle is moving in the direction of v, as you see, in that direction, at any point, it creates a magnetic field that it circulates around the velocity vector or the line that is in the same direction as the velocity vector. If you look from behind, this is the particle that's going into the page, and it creates a circulating magnetic field around it. The same goes for a element of current. It means a little piece of a wire, and that wire has a current I, and it has a small dl, and you said that instead of q times v, we can write I times dl, and you see that the magnetic field is exactly the same way, and B is given by mu naught over 4 pi I dl cross r hat over r squared. This is called Biot-Savart's law. It's similar to Coulomb's law for electric field of a charged particle. And again, if the current goes into the page here, the element of current is there, the magnetic field is circulating around it, and we said that we can use the right-hand rule to find out which way it is circulating. For example, here, is it clockwise or counterclockwise? In this case, it is clockwise, because if you put your thumb in the direction of the current, which is into the page, your right hand, you see that your 4 fingers shows the direction clockwise around it, as you see in here. You put your thumb in the direction of the current, and your 4 fingers show which direction the magnetic field is circulating around the current. All right, and then we said that when you have a long wire carrying current I, the magnetic field is circulating around it again. You can bend the wire and make a loop, and magnetic field changes like that. And if you have many loops, it has magnetic field like this, which looks like a magnet. And we said that the magnet has the exact same magnetic field because it is created. The magnet is made up of a lot of particles, atoms that have electrons going around them, or they have a spin. It is quantum mechanical, and you can imagine like the electrons from each atom is contributing in a current that goes around the magnet like this. All right. So in that sense, they are in fact exactly the same. And then that was, as I said, this is the subject of chapter 29, but now we come back to chapter 28, which talks about the effect of the magnetic field that already exists. We don't care how the magnetic field was created. It was created by some moving charges or current densities or current distribution. And now the magnetic field exists. It's here. And then we want to see what happens if a charged particle is moving at the velocity v in this magnetic field. The result is it experiences a force. The force is perpendicular to both magnetic field and the velocity vector. And therefore, it is perpendicular to the plane, passed over the magnetic field and the velocity vector at that moment. And therefore, it is either this way or that way, up or down. We said that you can use the right-hand rule to find out which one of these, up or down. And right-hand rule for the cross product tells you that if the charged particle is positive, the force on the positive charged particle is in the direction of v cross b, which is up in this case. If the v velocity is perpendicular to b, you get the maximum force because the magnitude of v cross b is magnitude of v times magnitude of b times sine of the angle between v and b, which is phi in here. And when the sine becomes 1 or phi becomes 90 degrees, you have the maximum force. All right, so this is just the same thing, but instead of sine phi, we have 1 because the angle is 90 degrees. And this shows the right-hand rule, how you can find the right-hand rule, find the direction of the force for any magnetic field and any velocity. Here it says, if you turn your 4 fingers from the velocity vector to b vector, because it's v cross b, and if the charge is positive, then F is in that direction that your thumb shows. In this case, you see this velocity is here, B is here. So if you want to turn your fingers from V to B, your thumb shows B down, right? And in each case, if the charge is negative, then you flip the direction at the end. So you see it, and in the top case, V cross B is still up, but Q V cross B, because Q is negative, is opposite. And also in here, if V cross B is down, but Q V cross B is opposite, so it goes up, right? Any questions? All right.
That makes sense.
Yes?
Oh, no, I was just saying there's no questions
Okay.
since so far.
All right. So here was an example. We said that this negative charge particle is moving to the right, and there's a magnetic field perpendicular to the page and into the page, and we show it by crosses, as I explained why we show by cross. And this is our notation. And then we want to see which direction is this negative charge particle, and if it gets deflected, which means that which direction is the force on that. So you see that if you do V cross B, V is to the right. If you turn your 4 fingers from the right to into the page, your thumb shows up, but the particle is negative. So that therefore, the force on that particle is down, and therefore it turns downward. So it goes on path 3. And then we said that if you have a particle moving perpendicular to the magnetic field, as you saw, it goes on a circle, and this magnetic force becomes centripetal force, and QVB becomes mv squared over r. You can solve this for r. So it goes on a circle with radius of mv divided by q times b. And you can also write v as 2 pi r over t, and then you can find a period of circular motion. It goes on a uniform circular motion if the velocity is perpendicular to the magnetic field to begin with. If the velocity is not perpendicular to the magnetic field, it has 2 components. One is perpendicular to the magnetic, one is parallel to the magnetic field. It goes on a circle because of this perpendicular component, and also because of this parallel component of the velocity, it goes forward or backward, depending on which direction that is. As it is going on the circle, it goes in one direction along the magnetic field. And therefore, it goes on a helical path, as you see here. All right, but the radius of the helical path will be given by mv perpendicular divided by qb. See, this was mv divided by qb. This has become mv perpendicular divided by qb. All right, and we said that this happens in the magnetic field of the Earth because the sun sends some charged particles and they come to the close to the Earth, and they get trapped into magnetic field of the Earth, and therefore go on these helical paths, almost helical, because you see it gets tighter as the magnetic field becomes stronger. See here, the magnetic field in the radius, the magnetic field is in the denominator. So when you get a stronger magnetic field, the circle becomes a smaller radius. So that's why you see here, magnetic field is weaker. We have a larger radius. It becomes smaller radius here. So when these particles hit the atmosphere here, they create lights that you see as northern lights or aurora borealis. And we did this example that was exactly using these formulas, as you saw. And then we talked about velocity selector. Velocity selector device has a magnetic field and electric field that are perpendicular to each other, and the particles come in the perpendicular to both of those directions. And we said that if the particle has a specific velocity in that direction, then the net force on it will be 0, and therefore it goes right through. But if the velocity is different from that value, either this one becomes bigger or this one becomes bigger, or therefore the net force is not 0, therefore the particle gets deflected. So because of that, this is called velocity selector. It selects particles that have exact velocity that's given by the electric field divided by magnetic field that is in the device. All right. Any questions on that? All right. Then we have Hall effect. And that is where we stopped. There is another a very interesting phenomenon that a graduate student called Hall figured out. And using that, we could find out that the electric current that we know is whether it's made up of moving negative charge particles or positive charge particles. So it makes a difference between if the moving particles in a wire or whatever we have currents in, whether it has positive charge particles moving in the direction of current or negative charge particles moving in the negative direction of the current. So he used a strip-like, it's a belt-like piece of copper. Like instead of a wire, we use a belt-like or stripe, like of the wire. So this is copper, and we send the current through it in the x direction. So we have Jx or current Ix going in this direction along the x direction. But the width of this is in the z direction, and the thickness along the y direction is very, very small. All right, so it's like a belt. And then we have a magnetic field in the y direction applied to this this belt, and it has current in the x direction. So now we can suppose whether we can suppose that the charged particles that are creating this current are positive. So if the charged particles are positive, then which direction should they move to create this current? they should move in the x direction, don't they? They should move in the x direction to create this current, because that is the current is charge that passes through the cross section, so it's in that direction. If it was negative, it would be moving in the opposite direction. So negative charge is moving in to the left is the same as positive charge is moving to the right for the current. It's the same thing. So now I'm going to ask you, if this charge is moving in the x direction and the magnetic field is in the y direction, what is the direction of force acting on it? What is the direction of magnetic force acting on it? So I want you to answer this question. And I raise the poll, and please answer using that. To the other room because personnel want to do something here while you're doing this. All right, so we have 80% of the answers in. Please answer. I think I'm making a lot of noise here. I will be right back. All right. So we have all different kinds of answers. I'm going to end the poll now and share the results with you. We have all different kinds of answer, but the majority of the answers are E, which is in the positive Z direction. Does anybody want to share their thoughts? All right, let's see. Excuse me. All right, Lance says right-hand rule, of course, but what was your answer? Yeah, all right. Yes, if you use right-hand rule, you put your 4 fingers in the direction of V and then turn into B, which is from X direction to Y direction, and then your force will be in the Z direction. Cross product will be in the Z direction. And because the charge is positive, the force is in the direction of V cross B. Or you can say I cross J is K. And so I cross J is K, so the direction of V cross B will be in the Z direction, positive Z direction. And because the charge is positive, it remains the same. So the answer is E, which was the majority of the most popular answer. Okay, good job. And now, any questions about it? All right, so if you want, I can turn on my camera and show you how to do that, but I think you understand from the figures. So the force on the charged particle is this. And as a result, when all charges are moving to the right and there's a magnetic field and all of them feel the force upward, what happens? The positive charge particle gather on the top of this, and there will be lack of particles, positive charges in the bottom. So it becomes like this. The top part of the belt becomes positively charged. The bottom part becomes negatively charged. And by putting a galvanometer between these 2 points, for example, connect the galvanometer from its top to the bottom, you can see which direction the current flows, and that shows which direction is positive. All right. So you can verify whether this is positive or this is negative by using a galvanometer. Now, what happens if we have the same scenario, but now the negative charge particles are moving? If the negative charge particles are moving to create this current, which direction should they move? Can somebody say?
Negative X direction.
Negative X direction. Yes, they should move in the opposite direction of current to create a current in that direction. So this is the direction the charge particles will move if they are making the current, right? And then what is the direction of the magnetic force on these charge particles? What do you think? Do the same thing. You want to do Q V cross B. So you see that V cross B is which way?
Negative Z.
Negative Z. And because the charge particle is negatively charged, then QV cross B will be again up, isn't it?
Yeah.
So in this case, the upper part of the belt becomes negative, the lower part becomes positive. And so you can do this experiment and see which side becomes positive, and that distinguishes between whether the charge carriers are positive or they are negative. The experiments show that it is the case that negative charge particles are moving. So the top part of the belt is negative and bottom part becomes positive. So the charge carriers are negatively charged. All right. So this is whole experiment. You know, before that, nobody knew whether the particles that are creating the current are positive or negative. And this was very important experiment that showed that the charged particles that are current carriers are positive or negative. They show that it was negative. And that's why you see that, you know, unfortunately, electrons are negatively charged. Historically, they called it negative, but they didn't know that this is the one that is moving around. The positive charges are not moving around. The positive charges are deep inside the atom, at the nucleus of the atom. Usually they don't move around. It's the negative charges that are moving around. That's why we have this negative problem that everything is opposite of what it should be. Otherwise, we would call the electrons positively charged and we go in the direction of current and everything would be good. Anyhow, so this is Hall effect that uses the this subject material, the magnetic force acting on the charged particles moving in a magnetic field. All right. Another application of this is mass spectrometer. You probably heard about this in some physics or chemistry labs. They do mass spectrometry that shows different masses of the different isotopes of atoms. In a mass spectrometer, we use a velocity selector, and the beam of atoms or particles come here this way, and they go through a velocity selector. So all of those that pass through here is a small hole. All of those that pass through this hole, they are they have the same speed. And then So the speed that they have is E over B. And then they go to another magnetic field that is pointing outward. You see, it's denoted by dots. This B is different from the magnetic field that's inside. It's another magnetic field. And because of this magnetic field, these particles go on circles. And remember, the circle had a radius of mv divided by qb. And now B present there is B prime. That's why I put B prime here. So they all have the same velocity. They all have the same charge. You know, they could have one electronic charge or two electronic charge. Charge is quantized, and they have either one or two. You can figure out beforehand what how many electronic charges do they have. So all of these are equal for for all of them, but the particle that has a larger mass goes around a circle with largest radius, and therefore they go hit this detector. This is a particle detector. They hit these particles at different positions because of different radii of orbit they have. And this is how they measure the mass of a particle when they know their charges. All right, and it's called mass spectrometer. So magnetic field separates particle by mass. The greater particle mass, the larger the radius of its path. All right, any questions? This is one, again, another. And accelerating particles in the cyclotron. Remember, we said that the period of circular motion for the particles that are going in the magnetic field is this 2 pi m over qb. You see, it only depends on the mass, the charge, and the magnetic field. It doesn't depend on the speed. Isn't it interesting? It doesn't depend on speed. It means the faster it goes, I talked about this, the faster they go on a larger circle. Therefore, the period for one revolution for all of them is the same. So, and the frequency is inverse of the period, which is qb over 2 pi m. Frequency doesn't depend on this speed, how fast they're going. So this may be very simple or interesting stuff, but some people are smart enough to use that to create an accelerator. So time, period, and frequency do not depend on speed. So people use that to create this cyclotron that accelerates particles. So let's say we have a source here, and we have these Ds. They call them D because they look like a D. They are a semi-discs. Actually, there are two layers of them, and the particles go in between the layers. All right, there's one layer behind and one layer from layer of these Ds in front. So the particle goes around, and this is connected to an oscillator. Means that this oscillator actually makes these Ds alternatively positive, negative. So let's say the particle is a positively charged particle, a proton. And then when it comes out, this side is negative and it gets absorbed into this side, but it doesn't hit any metal. It goes in between the two Ds and moves in perpendicular direction of the magnetic field that is present here out of the page. You see, these are dots are the magnetic fields that are out of the page, perpendicular to the page. So if the particle is positive, actually in this case, oh yes, if the particle is positive, you see that when it's going this way, there's a force this way, so it turns it in this direction. And as it is turning, now, because of the shielding effect, because inside the conductor, there's no electric force, it just magnetic force applies to that. You can change the this positive plate, negative plate to positive and make the other one negative. And then when the particle gets to this point, this side, the left side is positive, the right side is negative. So it accelerates through this gap to the other side. And then now it's going faster. Therefore, it's going on a larger circle. And then it gets here. And then during that time, the polarity of these again changes. So this becomes negative now, this becomes positive, then accelerates further to this side and goes on a larger circle. Again, accelerates, go larger, larger, larger until it gets to the deflector at the end. And then you have a beam of high speed particles. So this is an accelerator. The key point is that the time that it takes from here to here, it doesn't matter, that it is the same for all these circles. Therefore, if you keep changing the direction of the voltage, it keeps accelerating until it gets to this point. All right. So this is a cyclotron. Any questions? All right, so these are just easy applications. And then now these are, of course, high-level acceleration applications. We're coming back to basic principles again. What is the magnetic force on a current carrying wire? Now we understood the magnetic force on a moving charge. We want to see what is the magnetic force on a current carrying wire, a wire that has current in it and is in the magnetic field. So because the current is because of the moving charges, each moving charge feels a force, and therefore the current feels a force. Suppose we have this wire that has current I in it, and it is in the magnetic field. Sorry, magnetic field is this way, B field in this direction, and it has a length L. And you see, because the current is this way, means that it's like positive charges are moving this way. And you see that the force on the positive charges is perpendicular to both the velocity vector and B vector, which is perpendicular to the plane of this, which is, we can consider horizontal plane. So it could be up, could be down. From right-hand rule, we know that it is up, right? So this is the force on each particle and also on each on the wire itself. For example, if the electrons are moving, which is the case, the electrons are moving this way, and if you calculate V cross B, you see your thumb shows the downward, but because the charges are negative, the force is upward, so it doesn't matter. You can consider positive charges moving out of the page, or negative charges moving to the other direction. All right, so the magnetic force on a wire of length L carrying a current I, making an angle phi with the direction of a uniform magnetic field B, is given by this formula. Now, instead of Q V cross B, again, we put I L cross B, because QV, as I showed before, is the same as I times L, right? So we can write it this way. So if the length is L, and here we are actually defining a length vector, which is along the wire and in the direction of the current. So that is the length vector of the current of the wire. If you cross that by the magnetic field and then multiply by the current, you get the force on the wire. All right. This vector L has a length L and is in the direction of the current I. For a current element, DFB means the element of force of magnetic field is equal to I dl cross B. I is the current that goes through the current element, and dl is the length of the current element cross B. All right, so this is the force. And now if you want to calculate the total force acting on a wire that's not straight, and maybe the magnetic field is not uniform, then you have to write this, find this for each element and add up, which is the integration. Okay, you need to do integration, but I don't see where we do that. We don't usually do that unless we have to. All right, usually we deal with the cases where magnetic field is uniform and we have a finite length L. Like this, a straight horizontal length of copper wire has a current I equal to 28 amps through it. What are the magnitude and direction of the minimum magnetic field B needed to suspend the wire? That is, to balance the gravitational force on it. The linear density of mass per unit length of the wire is 46.6 grams per meter. So we want to see what are the magnitude and direction of the minimum magnetic field needed to suspend the wire. So we're going, we can draw the situation, draw the figure, see what we need. Suppose this is the wire. It has a certain length L, and it has a mass, so there's a force of gravity, mg, applies to it, and there's a current. Let's say the current is going to the right, or lowercase I. The current going to the right, and it has some mass. We want to see what should be the direction of the magnetic field to balance the gravity or the weight of this wire. So what do you think? Which direction should the magnetic field be in order for the magnetic force balances the weight? When magnetic force balances the weight, means that force of magnetic field is which way? It's up, right? So this is FB. FB should be up and should be with the same magnitude if you want balance. But now, what is the direction of magnetic field that creates a magnetic force like that? Which direction
into the page.
Sorry?
Into the page.
Into the page, yes, very good. Yeah, if the field is into the page, which we can show by crosses, now you see that if you put your 4 fingers in the direction of the current, turn into B, which is into the page, so it has, so this is B field, it has magnetic force upward. All right, so we found out the direction. It should be perpendicular to the wire into the page in this case. And now what is the magnitude of the magnetic field needed? So what is B magnitude? How do I do that? So this has a length L and has a mass M. So we say that the force of B should be equal to mg, right? But what is the magnitude of the force? Magnitude of the force was I L cross B, but L and B are perpendicular to each other, so it becomes I L B, right? And it should be equal to mg. But you see, we don't have, the wire has, we don't have the mass of the wire. We have the linear mass density, the mass per unit length. We don't have the mass. What should we do here? Let's say this is lambda, which is mass divided by length. So you see, if I put this mass divided by length, I get lambda. So if I put B, if I solve for B, B will be mg over Li. So this m over L is the lambda. So it becomes lambda g over I, right? So now we know lambda, and lambda is 46.6 gram per meter, or in SI units becomes 0.0466 kilogram per meter. And then G is 9.8 Newton per kilogram. That's kilogram. Let me write nicely. Didn't like that. So kilogram times 9.8 Newton per kilogram divided by I, which is 28 amps. Oh, kilogram per meter, sorry, is 0.0466 kilogram per meter. And so you see kilogram cancels out. So the unit of B becomes Newton per meter amp, which is Tesla. So you can multiply these numbers and get the magnitude of the magnetic field. How much do we get? We get about 0.17 millitesla. All right, or 170 microtesla. Make sense? Any questions? So this is a relatively large magnetic field. Microtesla is a large magnetic field. All right. Make sense? Any questions? All right. This is another example that says a strange horizontal copper rod carries a current of 50 amp from west to east. So this is from west to east. It has a current I the same as before. In a region between the poles of a large electromagnet. In this region, there is a horizontal magnetic field toward northeast. So magnetic field, this is west, this is east, toward northeast, that 45 degrees north of east. So the magnetic field is this way, right? At 45 degrees. So this is B. With the magnitude of 1.2 Tesla. So this is the magnetic field, and we have a current in that direction. Find the magnitude and direction of the force on 1 meter section of the rod, while keeping the rod horizontal. How would it be oriented to maximize the magnitude of the force? What is the force magnitude in this case? All right, so what is the magnitude of the magnitude and direction of the force on a 1 meter section of the rod? Let's say this is 1 meter. So what do you think? You can say the force is in which direction? Northeast, southwest, west, or east, west, north, south, or up or down. Up means we are looking from on this figure from above. So up means toward us, out of the page. Down is into the page. What do you think the direction of the force is? Can you tell?
Is it out of the page?
Out of the page, we win north. Yes, from right-hand rule, you turn from I to B. Yes, that's right, up. Very good. So the force will be, if you want, oops. If you want to show by dots, this is the force because it's coming out of the page. So that is the force. And the direction, what is the magnitude of the force? We say F is magnitude of the force is equal to, or FB is equal to the Q, equal to I, sorry, I, then the length L times B times sine of the angle between them, right? I is 50 amps, so 50 times L is 1 meter, B is 1.2, and sine of phi is sine of 45 degrees. So that becomes 60, right? 50 times 1.2 is 60 times sine of 45. Sine of 45 is the square root of 2 over 2. So basically becomes 30 square root of 2, or sine of 45 times 60 becomes 42.42 Newton. So 42 Newton from this magnetic field applies to 1 meter section of the wire or the rod. Sounds good? All right, now it says while keeping the rod horizontal, how should it be oriented to maximize the magnitude of the force? What do you think?
Turn the sine value to 1.
Turn sine value. How should we turn the wire? For example, from the way we are looking at it, should we rotate it counterclockwise or clockwise?
Clockwise?
Clockwise, yes. This angle is phi. We want to make the phi 90 degrees. So we move the, turn the wire, the right side, we need to turn down and left side up. So it goes in clockwise direction. So we should move it, in fact, to perpendicular to the magnetic field like this at 45 degrees below the so that it is the magnetic field is perpendicular to, so in this direction. So now it is northwest to southeast, right? And this B is from southwest to northeast. They are perpendicular to each other. So we need to turn it 45 degrees this way in clockwise direction. And what is the force magnitude in this case? The force magnitude is again ILB times sine of phi, but sine of phi is 1. So it becomes, instead of this, we have 1. So what would be the magnitude?
60.
It becomes ILB only, yes. ILB, which is 50 times 1 times 1.2 times 1, because now sine of 90 is 1. So it becomes 60 Newton, right? Make sense? Any questions? All right. Now, we want to see what happens if you have a loop of current. Imagine this, it's a busy figure. Sorry about that, but if you want to show everything on it, it is pretty complicated. So we have a magnetic field that is up in this case. Means that if this is a horizontal plane, the magnetic field is perpendicular to that. See, this is XY plane that is shown here, and magnetic field is in the Z direction. And this is a loop of wire that has current I. You see here, current I is going around like that in the counterclockwise direction, as you see. And each piece of this wire from here to here has a force acting on it. From here has a force. And you see that if the current on this side is on the top side of it is in the negative Y direction, in the Y direction, actually, Y is here, then the magnetic field is in the Z direction, the current is in the Y direction. You see that if you do V cross B or I cross B, you get the force in the X direction. So this force is in the X direction, you see, if you do cross product. So the force on this side is in that direction. The force on the opposite side, because the current is in the exact opposite direction, the force will be also in the opposite direction. So this force is in the X direction. This other force is in negative X direction, okay? And they have the same magnitude because the currents are the same, the magnetic field is the same, and the length is the same. And the force on this side, if the current is down this way, if you do I cross B, you see that the force is in the Y direction, right? And on this other side, the current is reversed, therefore the force will be reversed. So you see that these two forces, F primes and negative F prime, cancel each other. F and negative F also cancel each other, but they don't pass through each other. So that this F is at this level, and this one is at the higher level. So they tend to rotate the loop, right? And if you want to calculate how much the torque, it applies a torque, they apply a torque, and how much the torque is, you can calculate the torque. The F has a magnitude of I times A times B. I is the current, A is the length of this. You see this is A. A is the length in that direction, and B is the magnetic field. And you see, because the current and magnetic field are at 90 degrees, this angle between the current and magnetic field is 90 degrees, right? So, and in this case also 90 degrees. So we don't have a sine of theta because that's 1. And then the torque it applies around this point is force, and this force that I highlighted here this force times the perpendicular distance, which compared to this one is F times B. You see, this is B, which is this distance, times sine of phi, which is this distance. This is perpendicular distance to perpendicular distance of force to this axis of rotation. Suppose this one, you take this as axis of rotation, then yeah, this is the perpendicular distance of the force to the axis. All right, so tau is force times perpendicular distance, it becomes B sine phi. And then if you replace force by IAB, you say IAB, B sine phi. You have capital B means magnetic field. Lowercase b is the length of the side of the loop. So, and then you can put AB together, IAB, B sine phi. And what is AB? A is the length of the loop, B is the width of it. AB is the area, isn't it? So that's the area. So you can replace it by area. So it becomes I times area times B times sine phi. And so this is the result. The torque is I times A times B times sine phi. I is how much current going through it. Area, how big it is. B is the magnetic field, the strength of the magnetic field. And there's a sine of phi. And you see sine of phi, phi was the angle of this loop, this side of the loop with the horizontal. You see that there is the same angle between in this vector that is perpendicular to the loop and the magnetic field. So this is the same angle, the angle between the magnetic field and the mu that is perpendicular to the loop. So these are the same angles. So you can think of that angle instead of this angle between the horizontal plane and that, because that is a little bit confusing, but perpendicular to the loop is exact direction. All right, so when you see that in this case, the perpendicular to the loop is mu is 90 degrees to the magnetic field, right? So in this case, the torque is maximum when these two are perpendicular, because sine of phi becomes 1. And then when in this case, when mu and b are in the same direction, means sine of phi is 0 and the torque becomes 0. All right. So basically, if you have a loop of current like this, we say it has a magnetic moment like that, and the magnetic field wants to align the magnetic moment to its own direction, right? So in this case, the torque will be in this direction. So it rotates the loop in that direction so that mu become aligned with B. When the mu is aligned with B, the torque is 0. And if you move it the other way, if mu goes this way, there's a torque bringing it back to the alignment. So the magnetic field tends to align the magnetic moment of the loop with itself. So we in fact we defined the magnetic dipole moment of the loop. We define the magnetic dipole moment of the loop of current as a vector perpendicular to the plane of the loop with the magnitude mu equal to the current times the area, the current that's going through the loop times the area of the loop. And if the loop has n turns and each turn has a current I, then of course the total current becomes Ni times area. So mu becomes Nia. The direction of mu is determined by the right-hand rule. So if you have a loop like that and current going through it like shown in the figure, then the direction of mu can be determined by right-hand rule like that. You put your 4 fingers going around like the current through the loop, and your thumb shows the direction of mu. Okay, so mu is perpendicular to the plane of the loop, so it could be this way, could be the other way, right? Could be this way. But a right-hand rule distinguishes between these two. So it says that you put your 4 fingers of your right hand around the thing that's going around, the current that's going around the loop, and your thumb shows the direction of mu. All right? Does it make sense? In terms of the magnetic dipole moment, we can write now the torque. You see here, IA or NIA, whatever that is, will be, if there's n turn, NIA will be the magnitude of mu. And then we have magnitude of B, and then we have sine of the angle between them. Does it ring a bell? That becomes the magnitude of mu cross B, or in vector form, tau becomes mu cross B. So we can write the torque acting on a dipole moment of magnitude mu as mu cross B. Okay, so mu is a vector, B is a vector. We can cross them together and get the torque. And that torque actually turns the loop, tries to turn the loop in a certain direction. Right? So the potential energy of magnetic dipole in a magnetic field can also be written as U equal to negative mu dot B. So you see that torque is mu cross B, the potential is mu dot B, but with negative sign. Why is it negative sign? Means that if they are aligned with each other, if mu and B are aligned with each other, they are in the lowest energy. Means that that is the stable situation. If you make them anti-aligned, they have positive energy and they tend to go to lower energy. Okay. So that's the lowest energy. If they are aligned, you get to lowest energy, which is stable. It means that, again, the magnetic field tends to align the magnetic moment with itself. Any questions? All right. And application of this, either you look at it as a loop or individual wires here and here. You can see that there are forces acting on the loop if you send the current I through the loop, and you have the loop in the magnet, so that north and pole, north and south. The magnetic field of the magnet is from north to south outside the magnet. Inside it is from south to north, but outside is north to south. So B field is from north to south. And then when the current is in this direction shown, you see that mu is in that direction. Put your 4 fingers in the direction around the loop. Your thumb shows downward direction. So mu is that way. And now mu cross B is the torque. So if you do mu cross B, mean turning your 4 fingers from mu toward B, then your thumb shows this direction. That is the direction of the torque acting on the loop. And that means that if you put now your thumb in the direction of the torque, you see that your four fingers show which direction is the loop is going to rotate. It's rotating around in that direction. All right. So there are lots of right-hand rules. You can also say that this current that's going this way and the magnetic field that's going this way, I cross B, is the force acting on that, which is the green arrow here, is the force. This one is F on that side, and this green arrow is F on this side. So you see that this also tends to rotate the loop in the counterclockwise direction, right? And so when this happens, then this side comes up, the other side goes down, and then when they get to all the way up here, the current switches and this continues pushing in the same counterclockwise direction. So the loop rotates and rotates, and that is the principle behind the DC motors. Okay, you can watch videos on YouTube about this, and I used to find very beautiful YouTube videos, but right now I looked and I found the new ones, and they are not very good. But anyway, you can learn from each one. It takes each one is about 5-6 minutes and explains in details how this part, especially this, which is the commutator, it switches the current. As soon as this side gets up here, then the current's reversed. Then again, on this side, it's the force is always down. On this side, force is always up. So it keeps turning the loop. Okay. So that's pretty much everything that we wanted to talk about in this chapter. The rest is just doing more applications, just some examples. There are lots of examples here. I'm going through them one by one today, and next time we're going through the examples for this chapter, and then we move to the next chapter. Hopefully, I don't know if I have enough time to spend more than a week on this chapter, but I think it's important. All right. A circular coil, 5 centimeter in radius with 30 turns of wire, lies in a horizontal plane. It carries a counterclockwise as viewed from above, current of 5 amps. The coil is in the uniform magnetic field of 1.2 Tesla, directed toward the right. As you see here, this is the B field. Toward the right. Find the magnitudes of the magnetic moment and torque on the coil. As you see, magnetic moment is actually shown here. Magnetic moment is perpendicular to the plane of the loop, and therefore it is up here, right? And then what is the magnitude of it? So if the current is going this way, as shown, see, you put your 4 fingers of your right hand in that direction, your thumb shows up. So this is the direction of the magnetic moment. And what is the magnitude of that? Magnetic moment mu has a magnitude that is Ni times the area. If n loops, n turns, and each turn has current I, and we have Ni, the total current, times the area. So n is 30 turns. That's 30. This is n. And this is I. And this one is the radius that we can find the area from. So 30 times I, which is 5 amps, times the area, which is pi times 0.05 squared, right? So meter squared. Amp meter squared is the unit of mu because it is current times area. So you can calculate that. 30 times 5 is 150, and then 0.05 squared becomes a small number. Then you get the total. I think here I have the result. 0.0. Oh, why is it 30 times pi? It is radius 0.05, so don't need to. This 2 shouldn't be there. So let me see if I calculate it correctly. Uh, 0.05 squared becomes 0.0025. So this is 0.0025. It should be 0.05 squared, and times pi times 150. I'll get 1.178. 1.178. Because it says radius of 5 centimeter. Maybe I thought it was diameter of. You see that instead of that, I got 4 times smaller. So that was wrong. All right, so it becomes 1.178. And then the torque becomes 1.178 times 1.2 times sine of 90 degrees. The angle between mu and B is 90 degrees. So it becomes 1.2 times 1.2, almost 1.4 something, right? So you get, again, this should be 4 times bigger. This should be 4 times bigger. These are right, wrong. All right. And this example says the coil in example, the previous example, rotates from its initial orientation to one in which its magnetic moment mu is parallel to B. What is the change in potential energy? All right. Yes, the time is over. We'll leave that for later. All right. Any questions? Oh, by the way, I should give you a test on the previous chapters. I keep forgetting to announce that.